Hey everybody, my name is Calvin and welcome back to my channel. In this video, we're going to be covering 5 intermediate Python concepts that show up constantly in real software engineering code. The goal here in this video is to help you read production Python more comfortably and write code that stays clean as projects grow. We'll be going over a few examples for each concept, and we'll look at why engineers use these patterns. Before we dive into the video, I have a quick announcement that I'd love to share with you all. Have you ever wondered how the biggest companies in the world organize, sort, and analyze their data? It's from the work of data engineers. Data engineering is the backbone of modern analytics, business intelligence, and machine learning. Data engineers in the US earn around an average of $130,000 per year, with some even making over $200,000 annually. Hi, my name is Calvin Lin, and I wrote this book because this is something that I wish I had when I first started out. From databases, data warehouses, and real-time data streams, this book will give you a great foundation to launchpad your data engineering career. This is Modern Data, from Ingestion to Production. Available on Amazon, Apple Books, and Barnes & Nobles, so get your copy today. Yeah, I wrote a book. Hope you guys get the chance to check it out, and I'd love to hear some feedback if you have any for me. We'll start off with a list called nums. We'll initialize it like nums is equal to a list containing 1, 2, and 3. And we can go, and this can be any size list, but we'll just keep it simple and have 1, 2, 3 items in the list. And now we can create an iterator. The iter function gives us an iterator over that list. Let's initialize the iterator. We can call it it. We'll just call it iterator. And we'll set it equal to iter, and we pass in nums. Right here, this is our iterator. Now, every time we grab a number from this iterator, it moves on to the next one because it keeps track. How do we grab those numbers? We can grab it using a next call. Our next call pulls the next available value from the iterator, and each call will advance the iterator forward internally. So for example, we can call it like so, next, and we pass an iterator. Now what should this give us? This should give us 1 because it grabs the first item in nums. Run it and confirm. Now what if we called print next iterator again? You might think, oh, it'll just grab 1 again. But no, since it keeps track of our first next, we now grab the second value. And now that's 2, and so on, until nums runs out. What happens if the iterator runs out? Calling next will simply raise a stop iteration error. We can show that using a try block. So we can try another print next iterator call, and we can verify it by having it print no more values. Whoops. And we should expect, since we have no more things to grab from nums, this will give us no more values. Now let's move on to generators. A generator is a convenient way to build an iterator using a function and the keyword yield. Yield produces a value and pauses the function. The next time you ask for a value, the function continues from where it paused. Let's write a generator that produces squares from 0 up to n-1 and consume it in a few different ways. First, using next for the first few values, then converting the remaining values into a list. This shows 2 realistic consumption styles and makes it clear that generators are one pass. We can initialize our generator like so. It'll look a little bit like a regular function, but there's going to be one key difference. So we have a squares, define squares, we pass in variable n. Let's create a for loop for I in range n. and this will find the squares. And now instead of returning a value, we can type in yield. And this is our generator. Each yield returns a value, and it pauses the function. What do I mean by that? Let's create a variable called generator, and we'll set it equal to squares 5. We can grab the values from our generator in the exact same way as we did our iterator. So here, we can just simply trade out our iterator for a generator. It'll give us 0, because 0 times 0 is equal to 0. And then the next one will give us 1 times 1 is equal to 1. And now our next call to generator will give us 4, because 2 times 2 is equal to 4. Now that you see what's going on here, we can just print out whatever's left. Since we're going up to 5, we should expect to see 2 more calls. We can simply get the rest by typing in print list generator. Our list gen call here will consume the generator until it is exhausted. So we do that. This gives us 9 and 16, because 3 times 3 is 9 and 4 times 4 is 16. Now, what if we try to consume it again? We get an empty list because there are no more values to grab. As you can see, iterators and generators are very similar. Generators specifically are used for large or streaming data, reading a big file line by line, processing logs, iterating over database rows, paging through API results. You process values incrementally without loading everything into memory at once. Let's move on to the next concept. The next concept I'd like to cover is comprehensions for transformation and filtering. This concept is about creating new collections from existing data in a clean, readable way. A comprehension is a compact way to build a list or dictionary, and it's usually done by transforming each item, filtering items based on a condition, or both. You'll see comprehensions constantly in production Python because they're a natural fit for data cleanup, mapping values into new shapes, and creating quick lookup dictionaries. Say we had a set of raw names that includes extra white space or inconsistent casing. The result is we want a cleaned list, and we also want a mapping from each clean name to its length, because that's the type of small data prep logic we're going to be doing all the time. We'll initialize a list called raw names, and we can have names in here like Kelvin. As you can see, inconsistent spacing and inconsistent cases. We'll have someone named John, a couple extra spaces as well. And we'll have Ava. All lowercase. This will simulate raw data. Raw data usually never comes in clean, so this is something you'll have to do all the time. Now, let's work on our list comprehension. The list comprehension I'm about to create will do 2 common cleanup steps. We can initialize it like this. Clean names is equal to bracket name dot strip dot lower. Our strip call and our lower call will fix the inconsistent spacing and casing errors. And we can get name by simply iterating over our raw names list. And now we'll have a new clean list with these transformations applied to raw names. And we can print this. And we can see we've cleaned it up. We've given everything consistent spacing. We can do the same thing with a dictionary. What if we wanted a dictionary with the name and its length? It's pretty easy. We can initialize a dictionary that will have name, which is the len name for name in clean names, pass in our new list, and this one right here will give us a fast way to create a lookup table. Now we can print name lengths. And we can see we'll get the dictionary with its name. We'll get a dictionary with the name and its corresponding length. We can also do some filtering. Say we wanted to only keep names that were longer than 3 characters. Again, we can initialize a variable. We'll call it long names, and we'll set it equal to a list name for name in clean names if the length of the name is greater than 3. We can print long names. We can run this, and you'll see that only Kelvin and John stay because Ava is not longer than 3. The main thing to notice here is that comprehensions are pretty much building new collections. They really don't mutate the original list. Raw names will stay the same. Clean names is the new list right afterwards. The third concept I'd like to cover are functions as objects, higher order functions, and closures. This concept relies on the fact that functions are values in Python. You can store them in variables, pass them into other functions, and return them from functions. This matters because many Python features and libraries are built around passing behavior into other code. For example, sorting with a key function. Closures are a related idea. You can generate a function that remembers configuration from when it was created, which is a clean way to reuse logic without having to write repetitive code. We'll use one example, sorting structured data and customizing behavior. We can start with a list of user records. This will look like API data, dictionaries with fields. We'll sort by ID, then we'll build a reusable extractor function that can be used as a sort key. This shows both functions pass into functions and closure in one single flow. Say we had a variable called users, and we'll set it to a list of user records. It will look something like this. We'll have ID is 3, name, and we'll repeat this a few times. We'll use Eve this time. Now, we can sort this list of dictionaries by the field ID. We can do that by calling a method on users, users.sort, users.sort will sort the list in the first place, which meaning it changes the order of users directly and it returns none. After sorting, users is rearranged. Now in here, specifically, we'll want to put in key is equal to lambda. The key equals tells Python, when you decide the order, don't compare the whole dictionary. Instead, we want to convert each dictionary into a value that represents it, and then sort by that value. So the key function here is lambda u. Lambda u colon u ID. Basically, what this is saying right here, lambda u colon uid, is just a short anonymous function. For each user dictionary u, it returns u with key ID. Python evaluates the key for each element. For example, our first dictionary here, since our key is ID, our ID here is 3. This is our ID here is 1 and 2. What this will do here is sort those keys, 1, then 2, then 3, and then arranges the original list to match that order. So we can check this out by printing users again. And we'll run this. And we can see our original list of dictionaries, and now we'll see our sorted list of dictionaries. Let's make a reusable key function generator. This function returns a function that basically knows which field to extract. So we can define it like so. Def make field getter, and we'll pass in a variable called field name. Also create another function called getter within this that takes a record. I'll return record field name, and then we'll return the getter. This function here will return a function that knows which field to extract. Now, let's create a key function for sorting by name instead of ID. And we'll call it by name. Field getter, pass a name. And now we can sort by name using the returned function. Users.sort key is equal by name. And now we can print users now. And we'll see something like ID2 name Eve, ID1 name Calvin, and ID3 with name Noah. We can print this, and we see that's what we get. What to notice here is that make field getter returns a function. That returned function still has access to field name even after make field getter finishes. That's pretty much the closure here. And then we pass that function directly into sort, which is a higher order function piece. The fourth concept I'd like to cover are exceptions for reliable error handling. This concept is about handling error cases in a controlled way. Exceptions are Python's mechanism for saying something went wrong and normal execution cannot continue. In real programs, we can use exceptions in two ways. You can raise them when inputs are invalid, and you can catch them when you want to recover gracefully. This keeps your code reliable because you can separate the happy path from error handling and still provide clear messages when something breaks. We'll use an example where we try to parse an ID from text, and we enforce a rule that the ID must always be a positive integer. This is pretty close to real input validation you might do in scripts and services. We'll create a function called parseUserID, which takes in text, and we can do a try block. User ID is equal to integer text. If the text is numeric, it can raise a value error. We can do something like accept value error as error E. In the text from E. Now this raises a clear error message that includes the bad input. We can check to see whether or not the user ID is greater than 0, and if not, we want to raise a value error as well. And we can return an error message that says something like user ID must be a positive integer. Now we can return the user ID if everything executes successfully. Now let's try a few different cases. We can do print parse user ID, pass in 42, which will give us 42. This is a valid case. Now we can try a couple of invalid numeric formats. In this try block here, I want to use parse user ID on a string ABC. Obviously, as you know, this will raise this value error right here. And this will print the error. The error here is invalid user ID, ABC, which comes from here. And we can try another invalid input. Say we wanted to pass in -5 or -5. And now this will go through this try block right here. It'll pass this because -5 is a valid integer, but it doesn't pass our business case. -5 is not greater than 0. So it raises the value error. User ID must be a positive integer. We can print this, and we can see that we correctly fail. Exceptions let you stop the normal flow when something is invalid, and our try except blocks let you handle that failure without crashing your entire program. The fifth concept I'd like to cover is data modeling with data classes and type hints. The concept here is about representing structured data cleanly. When your programs grow, you stop passing around raw dictionaries everywhere and instead define clear data models. Data classes help you do that with minimal boilerplate. They generate constructors and readable string representations automatically. Type hints help communicate what each field is supposed to be, which improves readability and makes tooling like linters and IDEs more helpful. We'll model a small cart example because it's easy to understand and it shows why data classes are nice. We get a clean object, readable output, and a method for behavior that belongs to the data. From data classes, import data class. Now, we'll define the data class right here at data class, and we can have a class called cart item, which has the field name, which is a string, price, which is a float, and a quantity, int, equals to 1. Now let's define a class method called total, pass in self, float, we can return self dot price times self dot quantity. Now we can build a cart variable, which is a list of cart items. See, we had a notebook with a price of $2.50. We'll have 4 of those. And we had a pen that costs $1.25. We'll have 2 of those. And finally, can have a sticker that costs 50 cents. And say we'll get 10 of those. Now we can print each item so you can see the readable data class output. So for item in cart, we can print the item and the item total. We can run this. And when you can run this, and we see that it's a lot more human readable than what it normally would give us. Now let's aggregate the prices. So grand total is equal to 0.0, and we'll iterate through the items in the cart. And set grand total is grand total plus item dot total. Print grand total grand total, and we should get $17.50. We have our type hints. Name is string, price is float, quantity is an integer, and we have a data class, our class cart item. And those were 5 intermediate Python concepts you'll use constantly in real software engineering. Iterables and generators for efficient data processing, comprehensions for clean transformation and filtering, functions as values for reusable behavior, exceptions for reliable failure handling, and data classes for clean structured data. If you enjoyed the video, be sure to like, comment, and subscribe. Again, be sure to check out my book. Thank you for watching, and I'll see you guys in the next video.